Okay, ladies and gents, so what we're going to be doing today is you guys are going to be watching a lecture video looking at our last topic that we need to address before we take our test over Newton's laws of motion. So this lecture is going to be addressing the third law, a little bit more stuff about it and how that is interactions between objects are going to lead us to understand better in our next unit what's going to happen when objects interact in terms of energy. So what we're going to be looking at is momentum. So we're going to be dealing with Newton's third law. So for our notes today, we're going to be opening up our notebooks to pages 12 and 13. Okay, so that's the pages that are after the notes we took on gravity. So go ahead and open those. So what we're going to look at for today on those two pages are some examples of different types of motion related to objects as they interact with each other, and what that means for objects essentially when they collide. So what we are going to be doing here is taking some notes. I'm also going to go through a couple example practice questions with you guys that you'll put in your notebooks. And then with those questions, you'll need those to help you answer your homework questions that are posted on Canvas. So those questions, you can find them under this lecture video on the modules page on our Canvas site. So there, go ahead and answer those questions on a separate sheet of paper. Right? If you need lined paper, there's plenty of lined paper available in the classroom for you. And if you have any questions about this stuff, we're going to go over it in class on Wednesday. So make sure you write those questions down so that you don't forget what you were confused about if there was something you didn't understand today. Okay? So I'm going to go ahead and flip our notes over to the pages that we're going to be addressing. All right, again, we're on page 13. Okay, so we're going to start up here with our title. All right, so in this case, we're going to title our notes Conservation of Momentum. Okay, and that's what we're going to be addressing today, is concepts related to momentum. So I went ahead and put at the top corner the equation for momentum. Remember, momentum, or Newton's third law of motion, the law that states for every action there's an equal and opposite reaction. We will see that today as we address this conservation of momentum, is that we have momentum here, that's P. Remember, the units for momentum are kilogram times meters per second. It's different from force, right? Because kilograms times meters per second, right, we don't have that second square. Again, we have our mass, which is in kg, right, in kilograms, and our velocity, that's meters per second. Okay. So the question we want to hopefully answer at this is, how does momentum alter two objects when they interact with each other? So that's what we're trying to address as we go through momentum. Okay. So conservation of momentum. Well, conservation of momentum isn't going to actually occur until two objects are interacting with each other. So most of the time when we're addressing momentum, we're going to be looking at two objects as they touch. Okay? So when we say two objects are touching or interacting with each other, the word we like to use for momentum is we say those objects collide. Right? So they hit each other and collide. There's different ways the object could collide, and we'll talk about those different ideas. But first, let's define what a collision is. Okay. So the basic definition of collision that we are going to use is just when two objects with a momentum collide and interact. So two objects that have a momentum that are going to be interacting with each other. Okay. So remember, for an object that has momentum, it's going to have mass and it's going to be traveling a distance, so it's going to have a velocity and it's traveling that distance in a certain amount of time. So any object that is traveling, right, that has a mass is going to carry a momentum with it. Okay, and so it's through this momentum as objects interact that we're going to get that equal and opposite reaction that we see with Newton's third law of motion. Okay, so again, a collision is when two objects with a momentum collide and interact. Okay. So with this, I went ahead and diagrammed what's going to happen when we have two objects that are actually interacting. And we're going to be looking at the relationships of momentum, all right, so in its components of mass and velocity, and what those do as two objects interact. Okay, so go ahead and follow along with me as I go through these three diagrams that I drew out of how objects interact when they collide. Okay, so you have types of collisions. Again, we're only going to focus on two objects that are interacting and what's going to occur between them. Okay, so the scenario here, this first one that I have my two objects. I went ahead and labeled them A and B. Okay, so with these two objects, I drew an arrow that represents the direction in which those objects are traveling. Remember, momentum is going to be carrying a velocity. So if it has a velocity, remember velocity is different from speed because it carries a direction. So in this case, we have a direction, right? Our arrows are pointing where our objects are going. Okay? So here we have object A. It is traveling, right? So it's going a distance and it has a mass. So it's going to have a momentum. So here I went ahead and labeled the momentum as a little p with a sub A. Okay, so that's representing the momentum for object A. Okay? Object B too also has a momentum. Okay, so for object B, it's going to be traveling at a velocity, right? It has a mass, so thus it has a momentum. So let's say in our instance here we have object A and object B. They have the exact same momentum between the two objects. Okay, so that means the mass velocity ratio is equal to the mass velocity ratio here. So when those two objects collide with each other, what we're going to see is those two objects will essentially stop. Okay, so if you have two objects that have the same velocity, same mass ratio, right, when they collide, those objects will stop. Okay, right, they have equal momentum. So if they have equal momentum on each side of our equation, essentially we're going to get our objects to stop. The second scenario. What's different about this scenario is that we've kept our velocities the same. Let's say our two objects are traveling the same velocity, so say like 10 meters per second. Okay? But of those two objects as they are traveling with each other, one of those objects has a much lower mass. Okay, so it contains less matter, has a lower mass. Okay? Then say object B that has more matter and thus is a heavier mass. Okay? So if those two objects are going towards each other and then collide, okay, what happens is since this object has a lower mass and the velocities are the same, its overall momentum is going to be lower than the momentum that object B will have. Object B has more mass, right? So if we times that mass by the velocity, that means momentum will be greater. So as those two objects collide with each other, what you're going to see is that those objects are going to end up changing direction. So in this case, object B has more momentum. So when those object hits, that's going to cause object A to change its direction because it has less momentum. So momentum is going to be conserved in the sense that our object will travel in the direction that had the greater momentum. Okay? So again, an equal and opposite reaction. So as this object is colliding, it has much more energy, essentially. It's going to have a greater momentum. So since it has more momentum, it's going to push this object back in the opposite direction. Okay, so these two arrows are still going to be equal. Our momentums are going to be overall conserved. Okay, but as these two objects collide, the one with the more momentum will change the direction of the other, right? And you see that when any two objects interact with each other, right? If you have, say, like a bowling ball and a bowling pin, right, that bowling pin's momentum is much lower than that of the ball, so that ball is going to hit it, and then that bowling pin is going to get ricocheted away. Okay? So in this scenario, again, we're looking at the relationship of momentum. So in this case, we've changed the velocity. So the velocity for A is much greater than the velocity of B. Okay, so A is traveling much more quickly than B is. So given that their masses could be the same, again, object A is going to have a greater momentum. Since object A has a greater momentum, when they collide, what you would expect to see is that object A will win, right? It'll push the object and the object B will go in the opposite direction, the amount of momentum that it absorbed. Okay, so again, equal and opposite reaction to our changes. Okay. So these scenarios that we're seeing, again, are all dealing with the relationship of P equals mv. Okay, so this equation that we have up here. So an object's mass and its velocity is going to dictate how much momentum that object is going to have. So in a system, when two objects are interacting with each other like this, say colliding, right, those momentums will interact. The object with the greater momentum will be the object that will change the vector or direction of the other object. Okay, and that's going to be directly related to the amount of momentum an object has. Okay. So if you have questions about this, again, make sure that you write those down so we can address them in class. Let's move on and talk about what happens with our objects when they're colliding in terms of their overall momentum. So we've seen that objects collide, right? If they have the same exact momentum, those objects will stop. Okay, right? They're equal, right? So since they're equal, the opposite reaction is going to be nothing. They're not going to change, right? Versus these objects that if they collide, right, if one has a greater momentum than the other, right, in this case B is greater than A, the object will travel in the direction that's there. Okay? So one unique thing that's about momentum that kind of separates them from other stuff we've talked about is that we can actually calculate momentum of situations of objects before they collide with each other and then objects' momentum after they collide, right? And we can see what that does or what that changes in terms of the object's velocity, all right, in that situation, as well as the object's overall momentum. Okay. So what we say is that momentum itself is in a closed system. So if given everything that we know of, that we've learned of so far, like friction is gone, forces aren't acting on anything externally, if just two objects are going directly at each other and colliding, that momentum is conserved in that system. So the amount of momentum before the objects collide should be the same as the momentum after they collide, right? Nothing is lost. We're not losing any heat. We're not losing any light. We're not losing any energy. So our objects, as they collide, are going to stay equal. Okay? So we can actually draw this in an equation. Okay, so this equation may look really complicated, but it's not too bad. Okay, so all we are looking at is the momentum of our object before. Okay, so m1 v1. So this is the same as like momentum for 1. And this one we have m2 v2. Okay, and these things are added together. So this is a plus sign. Okay, so you have the momentum of your first object plus the momentum of your second object. So those are going to be interacting, right? So we're going to say they're colliding. That's what the plus is equal to. And that's before. That momentum before should be equal to the momentum after. Remember, nothing is lost, right? So we lose nothing. Since we lose nothing, our object, as they interact, should experience the same amount of momentum after, right? So the mass and velocity of our first object plus the mass and velocity of our second object should equal the values from before. Okay? So then you're probably asking, what is it that's changing then if our momentum before is the same as our momentum after? Well, it's the relationship between the velocities and the masses that might change. So for example, if you have two objects that are interacting here, object A is going way faster than object B is, right? When those two objects collide, the velocity for object A is going to change. It should slow down, and object V should go up, right? Those relationships are proportional. Right? This is a proportional relationship. Okay, so that means that the object's relationship as one goes up, the other will go down. Okay? And so we'll look at some examples of how we do this calculation here in a second. But you should remember that momentum is conserved. So the amount before should equal, this represents equal, draw that a little bit better. Right? Our momentum before should be equal to our momentum after. Okay? So the only thing that changes are the relationships of mass and velocity. Okay. All right, so let's talk about the two types of collisions that we might see in this situation. Okay, so if we have an object that's in a closed system, generally the collision type that we're going to be looking at is what we call an elastic collision. An elastic collision is where you have a complete transfer of energy from one object to another. Okay, so essentially you conserve the energy, you conserve the momentum, so those objects collide and they bounce off. Okay, or they collide and they go in the same direction. Okay, so our objects collide but they separate. Okay? So objects collide, bounce off of each other, objects collide or continue going together, right? Like say you've probably seen like a pool, right? An object hits that pool cue, right? Your white ball might still go forward, but the other one goes much more quickly away. Okay, so it increases its velocity. Okay, so objects collide and bounce off of each other. That's an elastic collision. Okay, so because they bounce, right? Think about elastic things, they are bouncy. Okay. That's different than what we call an inelastic collision. So inelastic collisions, again, are different. It's where we have an incomplete transfer from one object to another. So essentially what we're seeing when those two objects collide, right, so when we have our two objects collide, is that objects will like stick to each other, okay? So like think of like you're throwing mud at like a bowling ball, right? You throw that mud at the bowling ball, that mud is going to stick to it. And what happens is you end up changing the mass of the overall system, right? So if you change that, momentum is going to be changed. Energy may be lost and momentum may be lost. So in inelastic collisions, you might see those like in really bad car accidents, like when two cars get wrapped up on each other, okay, or like if you like throw Play-Doh at a wall, right? That's an inelastic collision, okay. So when objects collide and stick together. So the way they work is a little bit different than what we're going to see with an elastic collision, but we're just going to kind of focus on elastic collisions as opposed to inelastic. Inelastic can get a little complicated very quickly. So we're just going to stick to elastic type collisions. Okay. So the last thing that I wanted to talk about and address in terms of momentum is the idea of what happens when momentum changes, right? We have a collision, right? We have an object that's interacting with another object, they're colliding and then either bouncing off of each other or sticking to each other if it's inelastic. But when you change those, right? When you change an object's momentum, so its direction or its velocity, right? Remember, that's two ways we can change momentum, is that we get what's called an impulse. Okay, so an impulse. So when we change our momentum, we generate an impulse. Okay, and so we can actually calculate an impulse, right? An impulse is the same, and we use the letter J here for impulse. It's the same as a change in momentum. Remember, this triangle represents change. We saw that when we saw delta V, right? When we had a change in momentum, like here, or sorry, a change in velocity when we calculated acceleration. So here we have a change in our momentum. So that change, we can also write momentum as our mass times our velocity, right? P equals mv. So in this case, instead of looking at just velocity, right, we're looking at the change in our velocity. So what is our speed before and our speed after? So we take our final minus our initial. So the other way you can write this is m is delta v. Okay. So again, these are all units that we've seen before. Okay. We know momentum is equal to mass times velocity. We know that an impulse is going to be a change in that momentum. Okay, so if we know that it's a change in momentum, we can change this p into its other units, right? The two things that multiply together to make it momentum. So I have my mass times my change in velocity. So my final minus my initial. So J is equal to m delta v. Okay, so we're going to use this equation to do some example questions on our second page. Okay, so go ahead and take this page and we're going to flip to page 12 and we're going to look at an example dealing with impulse. So this is part of what you're going to be calculating for your homework. Okay. Alright, so let's look at our example for impulse. So make sure you leave room so that you can write out our equation and get all of our work. Okay. So in this case, let's say we have this scenario. Okay. So write down the whole of this question. So this is an example that you might be given to calculate impulse. So an impulse is, again, defined as a change in momentum. So what we want to do is see what is the change in impulse for an object whose momentum is altered after a collision. The object has a mass to begin with of 10 kilograms and it has been at 5 meters per second before the collision and is slowed down to 2 meters per second. Okay. So we have an object that had momentum. It has a mass of 10 kilograms and it began at 5 meters per second and it slowed to 2 meters per second. Okay. So if we look at our equation, right, what things do we know looking at this? Right? It's asking us to find what? It wants us to find impulse. Okay, so we're trying to find what impulse is equal to. We know that this has two velocities that are given to us, right? We see meters per second, that's a velocity. So for this velocity of meters per second, right, we know that one of them is 5 meters per second, and we know the second one is 2 meters per second. Okay, so if we look at those two velocities, we can probably, and based on this question, right, we know that the 5 meters per second was my initial velocity, and this would be my final velocity, so v sub f. Okay, so I know I'm trying to find impulse, I know my velocities, and the other thing I know is my mass. I know my mass is 10 kilograms. Okay. So based on that information, right, I notice that I have an impulse it's asking me to find, I've got a mass, and I have two velocities. So I'm probably going to use this equation, right, where my impulse is equal to my mass times the change in velocity, so Vf minus Vi. So remember when we're doing these types of equations, right, we plug in our variables that we know. This is why we write all our work, kids. This is why we do it all. We do it all the work, write it all. So we take that, we plug it into our equation. So here we have our mass of 10 kilograms. We take that value times our final velocity minus our initial velocity. So here we've got 2 meters per second minus 5 meters per second. So when we do our calculations here, we end up with a negative impulse. Okay. So you might be wondering, well, how can I have a negative momentum? Well, you can. Okay. So with impulse, when you see negative, all you are essentially seeing is that you have a change in direction. Remember, what does this V stand for? V stands for velocity. If V stands for velocity, that means that you have a speed and a direction. So if you change impulse and that impulse becomes negative, that is showing that when the object collided with the other object, it changed the direction. So right, if these two objects are coming next to each other, they collided, one went back the other way. Okay, so that's all that we're seeing. So again, what we're doing with this equation is the same exact stuff that we did with everything else, right? You find your variables, right, in the equation, right, and you get those variables based on the units. So if you know the units, you can plug them into your equation, right, that matches those to find the thing that you're asked to find. Okay. All right, so again, you'll have examples like that for your homework. All right, let's look at our last example. Okay, this is one where we're looking at our conservation of momentum. Okay, so we're looking at that longer equation. Okay, so in this scenario, right, it's asking us to find a few different things. So let's look at it. Okay. So it says that we have a 15,000 kilogram rail car, and that rail car is moving 2.5 meters per second. That rail car collides and couples with a stationary car. So by coupling, that means it latches onto. It latches on a stationary car with a mass of 12,500 kilograms. And now it's asking what the new velocity of our object is. So what velocity will it have? Okay. So one thing to think about with this collision, right? You've got two objects that are sticking on each other. Okay. So if they are sticking on each other, what happens to their overall mass and what happens to their overall velocity? If those two objects become one, those things are going to be added together. So we can see that when we solve for this equation. So keep that in mind. Okay? They become one object. Okay, so we have this equation, right? We have our momentum for object 1 plus our momentum for object 2. Momentum object 1, object 2 is equal to momentum for our object before 1 and object 2 after. So this is before, this is after. Okay, so if I'll write that down so you guys don't get confused. This is before our collision, this is after our collision. Okay, so let's plug in what we know. Okay. So we know that for object 1, that rail car, we had a mass of 15,000 kilograms, and it was going a velocity of 2.5 meters per second. Okay. Then we can add that to our second object. So we know that our second object has a mass of 12,500 kilograms, and it is times our velocity, which is 0 meters per second. So then we can compare that to what we know happened after. So we know after we have our object that has this mass of 15,000 kilograms, and we know that it's stuck together, and we have it added to an object that has a mass of 12,500 kilograms. Okay, so we have that together. Okay, so with our two objects, right, we can end up simplifying this. So here we have this number, 15,000 times 2.5, that gives us 37,500 kilograms times meters per second. Remember, this is a unit of momentum, right? Remember, this is a mass, this is a velocity. We multiply those together and get momentum. We add that to this, right? 12,000 times, or 12,500 times 0 is still 0, okay? Because when you multiply by 0, your number becomes 0, right? That is equal to this value. So if you see here, what I did is I took my masses and my velocities and added them together, right? So I know that this object is combined together. So my masses become 1, so I can add those together, and I can add my velocities together, okay? Because this is becoming one single unit that's traveling together, okay? So if I multiply those together, right, and get those, I get just that number times the variable. But if I add them together, I get this overall number. So to find my velocity, to get v by itself, I would take my value, divide by this 27,500 from both sides of my equation. Remember, this goes away because I'm just adding 0. So I take this value divided by this value, and I'm left with a total velocity of 1.4 meters per second. Remember, my kilograms will cancel out. I'm left with 1 meters per second because this is only kilograms right here times my velocity. Okay, so those cancel out, and I'm left with a velocity of 1.4 meters per second. Okay. All right, so that's it for this page with calculating these questions. Okay, so again, just to review, right, momentum is just an object that's in motion, right? It's got a velocity, it has a mass. When it collides with another object, it's going to react. And so we can calculate that using this equation, m1v1 plus m2v2 is equal to m1v1 plus m2v2 after, so before and after. So we can look at that equation to see how two objects collide and interact with each other. All right, so that is the end of the lecture, okay, and talking about the material. So you got the notes, you have 2 examples. You can use this video to go back if you need to listen to another direction on how to do that. So what you guys should do now is go to your questions that are posted on Canvas that you should be answering related to impulse, momentum, and calculating changes in momentum before and after collisions, okay? So you have examples that I want you to answer. So for those, make sure that you answer all of those questions, show me all of your work, all right? And if you have questions on these tomorrow, you need to bring specific examples, right? Don't tell me that I don't know anything. That's not going to help me help you, okay? So make sure that you have specific things that you're not understanding, okay? All right, so I'm going to leave it there. Again, if you guys have questions, let me know tomorrow when I'm back in class, or let me know when I'm back in class, and I will be there to help you happily, all right?